Another example from chapter 12.2 in some examples of static equilibrium, balancing a leaning boom. So the figure shows a safe of mass 430 kilograms hanging by a rope, negligible mass, from a boom. Dimensions A is 1.9 meters, B is 2.5 meters, that consists of a uniform hinged beam, M equals 85 kilograms, and horizontal cable, negligible mass. A, what is the tension Tc in the cable? In other words, was the magnitude of force Tc on the beam from the cable. Part B, find the magnitude F of the net force on the beam from the hinge. All right, so first off, this problem mentions a boom, and I have no idea what a boom is, but from context, apparently a boom is something like this hinged beam and a cable all together make up a boom. So there we have it, not just for dynamite, also for physics. Boom. So next up, as we're looking at this, I wrote down the things that we know: the mass of the safe, the rope is about no mass, to say negligible, those dimensions, uniform beam, its mass, and the cable is also about no mass, which tells us that we don't have to worry about the force of gravity acting on those things that have negligible mass. That's great. We want to find the tension in the cable and the force of the hinge. And it gives us some nice clues actually in those restatements of the problem. It says the force on the beam from the cable or from the hinge. So with that in mind, I'm going to stop sharing so you can make this a little more visible. And since it's talking about the force from the cable on the beam and the force from the hinge on the beam, that gives us a clue as to our system here. Where our system, we always want to define it to know sort of what we are focusing on as an object, and so then we can just focus on the forces that are acting on that particular system, the external forces to it. And so since they keep referring to things that are forces on the beam, that's what I'm going to focus on here. So I'm going to say that our beam is the system. And assuming this is built safely, then the system will not be down. So the tools we have to keep it all up is a balance of forces, balance of torques. So that means we need to identify all the forces that are acting on our system, acting on our beam. And there are several here, right? One is gravity. We have to figure out where it acts. Well, because the beam is a uniform beam, it has to act in the very center of it. So middle of the beam would be about here. So that's our mg. There's also going to be, let's see, some other forces. One, there's the safe pulling down in the rope. And so the rope is pulling down based on some tension in the rope. So that'd be T sub R or T rope. I'll just do it as TR. Now, as an aside here, you can figure out and show that TR is equal to the weight of the safe. And to do that, we'd need to consider just the safe for a moment. Showing my work a little more than I might otherwise, just to be safe. Hope you're rolling your eyes right now. So for the safe, there's TR pulling up, little or big mg pulling down. And so if this is balanced, if the safe is not falling or flying upward, then TR has to equal big mg. However much the safe is pulling down is going to create the tension in the rope. So that's another force acting on our system is TR. The cable is also pulling on it, and it's just going to pull away from it. So focusing on the beam, and we have this tension in the cable, TC. Note, TC is not equal to TR because they're two separate ropes or cables. They're not connected, so they're going to be different values. Finally, there's also this hinge, the fact that this beam is pushing against the wall. So at the very least, the wall is pushing back out. But because it's a hinge, because it's clamped onto the beam there, it can also exert an upward force to counteract the fact that the weight and these things are pushing down. So we don't actually know the direction of the hinge's force, but I'm gonna guess that it's something up and out. Move that out of the way. F hinge. It doesn't have to be along the beam, it can be some random direction there. So we've identified the forces here. And with F hinge in particular, I want to break it down because right now it's pointed at a random angle, and that's hard to work with in our tools of F net X, F net Y. So I'm going to break it down into an F hinge X and another F hinge Y, just to make it a little easier on myself for using Newton's second law. And I'm gonna, on that note, go to Newton's second law because it's a great place to start. Really simple equations once you have everything in X and Y components. So F net in the X direction must be equal to 0. So what are the forces in the X direction? Well, we have the horizontal hinge force that's in the positive X direction. And the only other force I see in the horizontal direction would be TC, and that's in the negative X direction. So this tells us that the horizontal component of the hinge has to be equal to the tension in the cable. Boom, super fast equation. Sweet. I'm gonna do the same thing with F net Y. That has to be equal to 0. So we look at the forces in the Y direction. We have the vertical component of the hinge. So F hinge sub Y is in the positive direction, minus little mg and minus T sub R all have to add up to equal 0. So this gives us some more information, right? That F of the hinge in the Y direction has to be equal to little mg plus TR, we remember, is also equal to, from the work in orange, is also just equal to big mg. So the vertical force of the hinge is equal to the weight of the beam plus the weight of the safe. And this is something we can actually calculate, right? Those are all known quantities. So we can plug in our 85 kilograms. And I'm going to go ahead and factor out the G. So plus 430 kilograms times our 9.8 meters per second squared. And we can calculate that end result. Let's see, I think that should come to the force H, okay. So yeah, that should come to 50 newtons. Cool. So that was relatively quick to get half of part B actually. And part A, we're finding TC. So once we find TC in part A, we're gonna have the other half of part B, the horizontal component of the hinge's force. So this is looking really good, except we don't yet have a way to find the tension in the cable. So we're gonna need another equation, but we still have one more. We have the balance of torques. Remember though, before we can use this equation, this one's a little harder to use, we have to choose where to put our axis of rotation within the picture. So thinking about the picture, we want to place it strategically to eliminate an unknown force. And while you can put it multiple places, your life will be significantly easier if you place it strategically. You might say the whole problem hinges on it. Hope you saw what I did there. Yep, might be dying inside. It's all good. We want to put it right at the hinge. Why is that? Well, if we put it at the hinge, then we eliminate two unknown forces because we don't know anything about the vertical or the horizontal force from the hinge. So yeah, we don't want those in our torque equation. We can get way more information if we set it there and then we just have the three others. So with that in mind, I'm going to try and work a little lower. And I'm going to also re-sketch my picture because it's getting a little bit busy up there. Lots of good ideas going on. But just with the focus on, I won't try and draw everything this time. I'm just going to focus on the forces that are acting about this hinge. So there we go. We have the tension in the cable, the tension in the rope that's equal to mg, the weight of the beam itself, which we said acts at the very center. And we've placed our axis of rotation at the hinge, so we don't even need to worry about the hinge itself. Okay. Now, this is one where we need to figure out, when we're using the torque equation, which form of the torque equation we want to use. Because we have several, right? We've seen the torque can be equal to RF sine of the angle between R and F. And for this one, they do draw in a theta up here, but then they don't tell us what theta is. So the fact that they don't give us that theta makes that less desirable, but we could always figure it out from the dimensions. And so that would work, that we could do it with the angle. What's even easier, however, is if we can use the R perpendicular. It's honestly my favorite approach. So R perpendicular times the force, using the moment arm to calculate the torque. And so for that, we're going to have to spend a little more time figuring this out. So I'll start with mg. My R to draw to mg would go from the axis of rotation to where the force is being applied. So it'd be along the beam itself. But my R perpendicular wouldn't point in that direction. My R perpendicular points anywhere along this line of action, which is the direction the force is acting up, and it's a perpendicular intersection with that from the axis of rotation pointed to it. So for this particular case, it would have to be horizontal to stay perpendicular to that. So this would be my R perpendicular for my little mg to get a perpendicular intersection with that line of action. Now this can also help clue us into what it would be for the tension in the rope, which is equal to mg, right? This is a vertical force, so our R perpendicular to be perpendicular is going to have to point horizontally. Orange, so we have a different color here. Right, so that's the R perpendicular. Now what is that distance? Well, if we look back at the main picture, it has labeled that the total horizontal distance is b. So for the orange R perpendicular, that's just equal to b. What about for the green one? Well, because it's a uniform beam, we know this is right in the middle, and so that's just going to have to be exactly half of b. So that's going to b divided by 2. There we go. Okay, I want you to think for a moment about what our last R perpendicular would be for this tension in the cable. Have you thought about it? Okay, well note the tension in the cable is pointing in the horizontal direction, so our R perpendicular is going to have to be vertical, going from the axis of rotation to that vertical line of action. So I'm going to draw it going straight up. And so this R perpendicular is going to match our dimension A. Tilt up for a moment. You see that the A is labeled for that vertical piece. And so this R perpendicular just matched that of A. Okay, so this is a lot of work in the setup, but now that we've been very careful with our setup, the torque equation is going to be a lot easier to work with moving forward. So let's see if we can do that. So the net torque is equal to 0. And we're going to consider the torques from these three forces. So I'm going to have the R perpendicular of little mg is b over 2. Sorry, I'm working in the margins here. Little mg. And that, notice, is causing a clockwise rotation. So that would be negative. And as we keep going, we would have the tension in the rope that comes from mg. And that's also causing a clockwise. So that's going to be a minus as well, with this minus b. And times the tension in the rope, which is just capital Mg. Great. And then finally, we have the tension in the cable, which is causing a counterclockwise rotation. So that one is a positive. It's A times the tension in the cable, which is what we are solving for. Whew. And all of this has to sum up to equal 0. Keep coming down. We're almost there. So we have, these are both negative, so I'm going to add them to the other side and keep this A times TC over here. So A times TC is equal to B over 2 times mg plus B times big mg. And then we can divide both sides by A, and we now can solve for TC. So that's now an equation that is entirely solvable. I might regroup it a little bit to help myself out. I'm going to pull out the B, the G, and the A to make it a little easier, a little more palatable for plugging in. So I could write this as B divided by A times G times little m over 2 plus big M. And now this is something I suppose I could actually plug into. So let's see, B is 2.5 meters divided by 1.9 meters times 9.8 meters per second squared times little m, which is 85 kilograms divided by 2 plus 430, which is massive, by the way. Take a moment to appreciate how much mass 430 kilograms is. That is something I do not want falling on me, even if it's just in humor. And so if we multiply all of that out, you should find that the force in the tension in the cable comes out to 6,100. Newtons. And once we know that, we can take it back, put that in the bank, to the FXH, because we know FXH, we know FHY. And so we're looking good here. But we need to get it, we know FXH, or F hinge H, is the 6,100 newtons, right? And we know Fy is 550, but we need to find the net force on the hinge. So if this is the force in the x direction, this is the force in the y direction, how do we find the net force? To get the net force, we are going to have to do some Pythagorean theorem, right? Because we can make a triangle here, and the x and the y components would be the two sides. The net would be the hypotenuse. So F hinge is equal to the square root of fhx squared plus fhy squared. Sorry, I've made a mess of that, filling that in there. But there we have it. That is our final step. And I'll go ahead and go back to sharing the main screen so we can see the nice, neat summary of the end results. All right, so here we have it, that when we indeed do set the rotation axis at the hinge, then we can sum the torques and find that TC is equal to 6,100 newtons. Balancing the forces tells us the horizontal force in the hinge is the tension in the cable, the vertical force is the 50-50, and when we combine those, it's something bigger, but not the same as just adding them directly together. It comes out to 7,900 newtons. So there we have it. You can see these examples are fairly involved, but they're also very straightforward. They follow a procedure. It's a procedure we've seen before. So I encourage you to follow the math and take the challenges on. Ask questions in office hours or in the discussion session. I would love to help. So take care. See you soon.